Good afternoon.
Sure.
Okay, I hope I'm audible. So I just want to start by quickly mentioning what we did last time. We looked at an example of a discrete distribution, specifically the Poisson distribution, which is used to model rare events. So the probability of a random variable assuming a particular value, which could vary from 0, 1, 2, and so on. It denotes the number of events. So it has to be a whole number, is given by this exponent of minus lambda times lambda power I divided by I factorial, where lambda is the average or mean value of the random variable. We also saw the uniform random variable, which is an example of a continuous random variable, where the chance of the variable taking any value between alpha and beta, between the lower limit and upper limit of any arbitrary range, is same, meaning all values are equally likely. This distribution is the analog or the continuous version of throwing a dice, and the dice having equal chance of taking different values, or you're getting a number of equal chance. So this uniform random variable is something I asked you to use to compute the area of a shape by drawing a square around it and by randomly sampling points in the square and checking whether if the randomly chosen point is within the chosen figure or outside the chosen figure. We can calculate what would be the area of that shape. It could be a circle, it could be an ellipse, it could be an arbitrary shape. As long as we are able to draw a square and sample points around the square, we can compute that area. Uh, did did you all try using this MATLAB code that I posted and try playing with it? Would any of you be willing to speak or say what you learned by playing with the code? Or what you tried, what came out of it? That'll be a good start. Did you try running this code? Did you see anything at all? Were you confused? Were you um, enthused by something that you saw? Okay. So I could spend some time running this code and showing you some lessons. Yes. Changing n to lower number gives worse resolution, so area is not as accurate. Nice. So if you don't do enough number of trials, if you go back here, I wrote a formula for the area of the shape equal to the number of success events, which is the chosen points lying within the circle, divided by the total number of events, which is chosen randomly in the square. If you do very few total number, let's say you do only 10, the chance of something falling within the circle is even smaller. So I will be choppy. If you try it one time, you might get 3. You might try it another time, you might get 4. It might not be an accurate value. So as he says, as Nathaniel says, the key to getting accurate value for the area is to increase the number of trials to as large as possible. And I can show you that very quickly. Let's say we do only 10 trials and we have a square of side 2, which runs from -2 to +2. And we are trying to compute the area of the unit circle, whose area is equal to pi, or 3.1416. Okay. So with only 10 trials, okay, if I run this, I'm getting a success value of count value is 8. So 8 out of those 10 times the chosen points were within the circle, and the error I'm getting is about -1.85%. If I do again, if I run this again, This time I'm getting a difference of around 14.59%. I hope you can see this, minus 14.59%. In this case, only, 9 out of 10 values were within the circle. Okay. So this accuracy can be made, this difference between the correct answer and the obtained answer can be made arbitrarily small by increasing the number of trials. So you make 100 trials, it's within 10%. So you can check that by running it repeatedly. And each time it's around plus minus 10%. By making 1,000 trials, we can bring it to within a percent. So if I do 1,000 trials, I can get the answer down to nearly 1 decimal point accuracy. If I do 10,000 trials, I'm down to 2 decimal points. So 3.1416 is the true value. I'm down to 3.14. So it's less than a percent or less than half a percent. And if I do 100,000 trials, I can get to even closer. So it gets better and better as you do more trials. That's a good observation. Thank you. You should try with different shapes within the square, or you should try varying the size of the square. You should try varying funky shapes or things that are, let's say you want to get the area of a triangle bounded by 3 straight lines. You can do those, or you can do stuff like, let's say, you want to get the area of a shape which is bound by a straight line, another straight line, and then a circle on the third side. So you want to know what is the area of this pi, where this is a circle. Let's say it has a general equation x squared plus y squared equal to r squared. This is a straight line. We'll call it y equals m1x plus b plus b1. And this is another straight line, y equals m2x plus b2. So if I tell you the equation for 3 curves, and if I select, or if I choose, let's say, a box that is drawn arbitrarily around this, extending from minus L to plus L and minus L to plus L in each direction, and this is x, this is y. Okay. Now, if I randomly choose a point, we'll call it x naught and y naught. How will you check whether x naught and y naught are in this shaded region or they are not in the shaded region? How will you make that determination? So if I give you any point x naught and y naught, you can substitute that in this equation. If it turns out that this turns out to be greater, it means it's above. If it turns out to be lesser, it means it's below. Same thing you can apply for the second equation and the third equation. Ultimately, you have to decide whether this point should be drawn here or somewhere within the shaded region so that you can replace it as a if condition here. Now, this is the critical part. If you are able to convert a point, check whether a point is within or outside the shaded region. That becomes an if statement that goes in here, and then you increase the count or decrease the or not increase the count depending on the value. So again, none of this will make sense if I just say this and you never try it. So it's really important that you take this code and actually try it with an ellipse or a circle or other shapes. Okay. Unless you participate, this learning will not work. It will, if you are kind of expecting that all the concepts be provided to you in words and writing, there is not enough time to do that. You have to try things on your own, and then you have to come with questions or some kind of insights. Unless, I mean, I don't want to do this like a high school type setup where I kind of hold your hands at every step. I want you to try this. So hopefully by next lecture, at least somebody would have tried and tell us what they tried or show some results. Okay. All right. So moving on, I want to talk about the next topic in our discussion, which is continuous normal distribution, which is another important example of a continuous distribution. We already are very familiar with this from daily life. We talk about grading curves, the bell curve, distribution of heights, a lot of quantities. If you just measure them, they'll follow approximately a normal distribution. Okay. So if I go in here, here's the classic figure. Okay, I'll just paste it here so that we have some reference to go by. Okay, from observation, a large number of data or trials can be generally summarized using the probability density function known as the normal distribution function. What is that function? It's f of x. If f of x is your random variable, the probability density of x is given as f of x equal to 1 over, stop annotating. Yeah, 1 over sigma times square root of 2 pi multiplied by exponent of minus 1/2 x minus mu whole squared divided by sigma squared. All right. Okay. So this function is the distribution function where x can take values that range from minus infinity to plus infinity. Okay. And sigma obviously has to be a positive number because it's the standard deviation. And mu is called the mean. So we'll write mu is the mean or average, and sigma squared is the variance. Okay, quiz question. What is the probability that x takes a value in the range x to x plus dx? Okay, is it f of x or f of x dx? A or B? What's your choice?
F of x dx.
F of x dx, right? So remember this, f of x dx is the probability. F of x itself is called the density function. You get it's like probability per length of x. If you only multiply by dx, you get the probability that x will assume a certain value. So that said, if I want to know some more follow-up questions, okay? What is the sum of all the probabilities for the possible values of x? That is, if I sum x from minus infinity to plus infinity, what do I get? Come on, unmute, talk. 1.
Get the
One.
cumulative density function.
cumulative density function, if I sum everything, I'm going to get 1. Okay, that's the definition of cumulative function. Good. Okay, some more quiz question before we start doing some problems. Okay. All right. What is the probability that x takes values greater than 0.5? If I ask you such a question, what's your answer? What mean? I don't need numbers. I need an expression. What should I calculate? X takes values greater than 0.5. Probability of x greater than 0.5.
Would you change the range now to be the lower bound be 0.5 and the upper be infinity? So because it's
Very
anything above it?
nice. Very nice. So that's 0.5 to infinity. That's probability of x greater than 0.5. Okay, good. What is the probability that x assume values minus 0.1 to, let's say, 1.3? Thank you, Sandy Pon. What will be the answer to this? Minus 0.1 to 1.3. Extending what Jonathan said, lower limit will be minus 0.1, upper limit would be 1.3. Is everybody okay? You just have to sum the function between said limits. You can use your thumbs up to tell me that you're doing okay if you don't want to talk. Okay, good, good. Sean, what's up? Any question? Oh, you're just saying you're doing okay. All right, good. Okay. We also talked about the cumulative distribution function. Cumulative distribution function. Just recapping, we already talked about this. F of x. If I say f of x equals 0.5, that's like saying I want to sum all the probabilities from minus infinity to 0.5. So minus infinity to 0.5. This is nothing but the probability of x less than or equal to 0.5. Okay. All right. Here's another question. What is the probability that x assumes an exact value of 1? What is the chance that a continuous variable takes on an exact value of 1?
It's 0.
0. It's not just for 1. The value of any exact value, like 2, 3, 4, something that is precisely one a single value is 0, because the random variable cannot take on precise values. It has to take continuous values. If somebody asks you what is the chance that x equals 1.1, you don't have to do any integral. You can just say 0. Okay. So probability of any particular value is 0. Only the probability that x takes on a certain range, let's say minus c less than x less than c, is non-zero. Is basically this. A, B. By the way, somebody asked me through email, what about if this is integral a to b of f of x dx? What about probability of a less than or equal to x less than b? What about probability of a less than x less than or equal to b? Or what about probability of a less than or equal to x, b less than or equal to x? Are they all the same? Question to you. Are they all the same? Yes or no? No. Okay. All right. The answer is, in theory, they are all different because they also include the endpoints or don't include the endpoints. But in practice, when you want to compute, since the probability of x assuming a particular value is anyway 0, it's like adding 0 to one of these. So you always calculate this. Whether you are asked any one of these four, the answer is always computed as the integral, whether it includes the endpoints or not. Okay, so the answer is always the integral. Okay, all right. So now you also know this, right? You also know percentiles. We already talked about those, and you also know about median. Okay, now I want to talk about this function here. Okay, I want to talk about this function. Okay, talk about this function. If you look at this function, okay, sorry, if you look at this function, where does this function have a maximum? Just look at the formula and tell me where will this f of x be maximum, and what will be the like what will be that maximum value? This is an exponent function. It's positive function. It cannot be negative, number one, because these are all real numbers. And if you set, if there is a negative sign, and if x is anything other than mu, this number will be positive, which will make this function less than 1. So the maximum value of this function is 1. And the maximum value of this f of x will be 1 multiplied by this positive number. So if I draw a curve, what's the location of this peak? Where is this peak going to occur? At x equal to mu. And at x equal to mu, this top value is going to be 1 over sigma times square root of 2 pi. Is that okay? I'm just making a very simple argument that this function reaches a maximum at x equals mu and can only decrease either way.
Yeah, that makes sense.
Okay, if that makes sense, all right. Mu can also be thought of as a location parameter, meaning it locates the curve. Wherever x equals mu, that's where the curve is centered. The curve is centered around x equals mu. Okay, curve is centered around x equals mu. Now sigma is not only the standard deviation, or sigma squared is the variance. It is also called the width parameter. It decides the rate of drop of the function from its peak value at x equals mu. X equals mu. Why do I say it decides the rate of drop? If sigma is very large, you can have the function drop precipitously fast. If sigma is very small, or if sigma is yeah, if sigma, sorry, I got it backwards. If sigma is small, the function will be narrow. And sigma is large, the function will be wider. So as your distribution widens or narrows, it depends on how big is the standard deviation. So this direction, this curves is basically increasing sigma. It'll make sense when we do some example, which I'm going to do right in a minute. So let's consider a special case called the standard normal distribution. That is for the case where you have the mean value to be 0 and the standard deviation to be 1. That is, I want to consider f of x equal to 1 over is there a question? So if this is f of x, okay, I'm going to write f of x is now equal to 1 over square root of 2 pi times exponent of minus x squared over 2. This is a special case. This is a special case of the normal distribution, which we will explore. And once we know how to use it, any normal distribution problem can be reduced to the standard normal distribution. We'll see how. Are you with me so far? We are just considering a special case, which is for which we can do calculations much easily than doing every problem like a different problem. Okay. All right. So let's take this standard normal distribution. Okay. I want to so for remember for this distribution, your sigma is 1. Okay, your sigma is 1. And I want you to go back a few lectures where we did a test for normality. And one of the tests was if 68% approximately, if 68% of the data lies between plus minus, sorry, it lies between mu plus minus 1 sigma. That's the first test for normality, that 68% of the data lie within 1 standard deviation of the mean. Okay. We are now going to figure out where did this 68% come from. Okay, that's what we're going to explore right now. In our case, mu is 0, standard deviation is 1, which is like saying if it lies between plus minus 1. Okay, now how do you check or how do you estimate the probability of x lying between or minus 1 less than x less than 1? You know this, you just told me the answer. You know this. That'll be.
Is it the integral from -1 to 1?
Correct. So that'll be probability of, in this case, we'll do minus 1 to plus 1. Thank you. So that will be x equals minus 1 to x equals plus 1 of f of x dx. But you know what is f of x dx? You take this function, slip it in here. You need to evaluate this function from minus 1 to plus 1. If you can do this, you can then see whether this probability is really the 68% we were talking about previously. Elijah, do you have a question? Elijah Sorin?
Could you go back and explain how, like 2 slides back?
Here?
Could you explain how that exponent equals 1?
Oh, okay. So if you take x equals mu, that is at x, so I should say, this function equal to 1 at x equals mu. So if you substitute x equals mu, this is 0. What is exponent of 0?
1.
That's what I wrote here. Is that okay, Elijah?
So
on
at the
X
peak,
is
go ahead.
go ahead. No, you go.
Elijah,
Oh,
please,
so at the
let's finish
peak, it'll
this.
equal 1?
Yeah, no. At x equals mu, this function takes a value 1, and this f of x takes the value 1 over sigma times square root of 2 pi, and that is the peak value. Anything else will be even only smaller than that peak value.
Okay, I understand.
Bradley, quickly.
So basically the max value when is at x equals to mu.
Yep.
Okay.
Anything else will only be smaller. That is the highest probability. That's why it is called the mean. It's where it's most probable. Okay. All right. So we want to calculate the probability that x will take values between -1 to +1, and that is this integral, which if you do some very quick simplification, that's like writing 1 over square root of 2 pi times. This is an integral. You guys are getting ready for your prerequisites quiz. So you will tell me that this is nothing but 0 to 1, 2 times this integral. So I have to evaluate exponent of minus x squared by 2 dx from 0 to 1. If I can do that, we'll be ready to answer that 68%. With me so far? Yes, no? Okay, good. So we don't want to do integration. It's sort of messy and it requires a lot of math, but there is a quick table that you can see because people have numerically evaluated this integral and they have tabulated it for you. So I'm going to bring up that table. Okay. And I posted this on Canvas. If you see the Canvas, you can find it. Let's see Appendix A1. This is part of that Ross textbook. So here is this function where you have the integral for -infinity to x of e power minus y squared by 2 dy times 1 over square root of 2 pi. So they have already done this integral. So let's go back here. Let's just stop here. Now, what I'm saying is we want to use the appendix A1 to evaluate this instead of doing it ourselves. You understand the mission? We want to use the table to evaluate this. With me? Okay, I'm going to do some tricks now. All right. So look at this. Let me just take a screenshot of this function so that I'll have something for reference. Okay. This is what that table provides. Okay. What I want is not exactly that. What I want is this. Now, my question for you is, how can I write this integral that I want in terms of what is available? Can you do some trickery to see whether you can write this in terms of this? Okay. Think for a second. I'll give you the answer. So if you think about the cumulative distribution function f of x, what is f of x? F of x is -infinity to x minus infinity to x, f of x dx. Okay, that's what they have plotted here or calculated, tabulated here. Okay, it's nothing but minus infinity to x of this function, just that they have used a different variable inside. They use dy, and it's perfectly used dy or dx because it's just a dummy variable. It's just a name. So I can write it this way. And what I will have is the probability that x takes values that are less than or equal to x. Okay. All right. Now, if I want probability that minus 1 less than x less than 1, I can write this as f of 1 minus f of minus 1. I'm throwing that at you. You tell me whether if it makes sense or not.
It makes sense.
Thank you.
I don't see it. It doesn't
Okay,
make sense.
let's draw it for you. So if you take the entire range, okay, what is this? If I draw a line at x, this is all the area to the left of x. That's okay? Can you say that?
Yeah.
Okay. Now in this expression, I want to know what is the area contained between minus 1 and plus 1. So that's like saying I'll take all the area to the right of to the left of plus 1 and subtract all the area to the left of minus 1. I'll be left with what's between minus 1 and plus 1. That's all this statement is.
Okay, I see it now. Thank you.
Okay, so if you take probability of minus 1 to plus 1 to be equal to f of 1 minus f of minus 1, this is like saying in the notation of this table, they used phi, another variable. We can that's basically uppercase f in Greek. So we can write where is phi? Phi. All right. So this is like phi of 1 minus phi of minus 1. So I just have to go back to the table, look up phi of 1, phi of minus 1, put it in here, and I'll have my answer. Shall we do that? I want x equals 1 and x equals minus 1. Let's first look for 1. 1, 1.0, 1.00. So this is the first value I'm looking for. And then I want, so hold on here. I want phi of 1, that is this. I want phi of minus 1. Okay, that's a little tricky because this table has only positive values. It doesn't have negative values. So we have to think, how will we do phi of minus 1? You see the problem? So at least for phi of 1, we have the answer. It's 8413. That is this value here. Is everybody cool with that? For phi of 1, we have 0.8413. Yes. OK, good. Let's see. Let me look at the other screen in my Madison, Daniel, Rashid,
I have a
Caleb. Yes.
So this is isn't 1.00 a very exact value? Like, isn't that supposed to be a 0 probability?
No. We are asking what is the chance that x will lie between minus 1 to plus 1. We are not asking for exactly 1.
Oh, okay, got it.
Okay, let's think about this phi of -1, and we have to now understand how to use the table for negative values of x, which is not exactly straightforward tabulated, but we'll have to do a little mathematical trick here. Okay, so we are still left with trying to figure out how to get phi of -1. Okay, what is phi of -1? That is, if you go by this definition, that is minus infinity to -1 minus infinity to -1 of this function. Okay, minus infinity to -1. Yes. Okay. Minus infinity to -1. Okay, good. All right. What do we know about this this curve that we can make use of? That is, if you think about this bell curve, what do you know about it even without doing any sophisticated math? If it has a center at 0 or a mean value of 0, and it runs from -1 to +1, sorry, minus infinity to plus infinity. This is minus infinity, this is plus infinity, and we are interested in this -1. We already figured that if you draw the line at 1, the area to the left of that is 0.8413. We already did that calculation. How much is this area? That's the question.
Close to 0?
It's not close to 0. It's
It
some
should be
finite.
negative, right?
Area cannot be negative. What you're saying is the domain is negative, but area is not
Yes.
negative. So my question is, what else do we know about this distribution?
That it'll all add up to 1 since it's normalized.
It will add up to 1, but yes, that is true, but that's not going to help us here. What else do we know? Symmetric, Sandy Pond, thank you. Area to the left of -1 is equal to the area to the right of +1. I think that's what you mean. If you were to draw this here, this area is also same as this area. I think that's what you mean here. Okay, good. All right. Okay, it is symmetric, which means to the left of this line, you have 50% of the probability, and to the right of this line, you have 50% of the probability. Do you agree? Yes? Okay, good. All right. So to the right of this line, you have 50% of the probability, and up to here, that is from infinity to 1, you had 84%. That gives us some clue. So how much is contained? So this is 50%. Okay. This is 84% or 8413. This line is 0.5, which means how much is this line? How much is this zone or this area? If everything to the left of this line is 84%, is everything to the left of this line is 50%, how much is between 84 and x equals 1 and x equals 0?
0.3413.
The difference between the two, that is this horizontal line is 0.8413 minus 0.5. Is everybody okay with that? If you're okay, we can move forward. Let's see here. Michael, Chase, Brian, Brian, Bryan, Thomas, Emiliano. Are we okay? Ansar? All right. So everybody agrees that this horizontally dashed line is 0.3413. Okay. And by symmetry, this side should also be 0.3413. So if I draw a line here, this is also 0.3413. So the answer to our original question is what's contained between -1 to +1? Well, that must be 0.8413 minus 0.5 times 2, which is going to be 0.6826, or about 68.3% is contained between -1 to +1. That's where we got this number for test of normality, that approximately 68% of the data should lie within one standard deviation. Did that train of thought make sense to you? You have to exploit not only the integral, but also the symmetry of this curve. This is what problem solving is entirely about in this topic. Looking at this, converting a equation statement into a graphic and sketching the area, and finally figuring out the area. That's the problem template.
Can you re-explain how we know to subtract 0.5 from the 0.8413?
Okay. All right. Step one, you know that the bell curve is centered at 0.
Right.
And you know that this curve is adding up to 1, and it's also symmetric, meaning 50% is contained to the left of 0 and 50% to the right of 0.
Okay. And
Okay.
that's where the 0.5 comes from.
Yeah, and x equals 1, that table told us to the left of this x equals 1 is 84.13% of the probability or area or data. So if to the left of this line is all 84%, to the left of this line is 50%, then what's in between them should be 34.13%.
Gotcha. Thank you.
And if it's between 0 to 134.13, then between -1 to 0, that's like literally, hinging this sheet of paper at this line and flipping it about the vertical axis. That's this line. So this is exactly this flipped 180 degrees. So this should also be 34.13% by symmetry. So what is contained between -1 to +1 should be this plus this, which is 68.26. Thank you. Thanks for the question. Everybody is now clearer?
I want to ask about the bounds. Are they 1 and -1 because it's within ±1 standard deviation?
Yes. And the reason I use 1 here, because I'm dealing with a special case called standard normal distribution, for which mean is 0 and standard deviation is 1. But all the arguments that you make here can be extended to the case where mu is some arbitrary value and sigma is some arbitrary value.
Okay, I got it.
So instead of saying -1 to +1, we will say -1 sigma to +1 sigma. Instead of saying, assuming mean is 0, we'll say mu plus sigma and mu minus sigma. That's all.
Okay.
Okay, let's attempt a problem. All right. I mean, once you get this hang of this, it really becomes straightforward. Okay. All right. Let's try problem 23 from the textbook. Okay, it's just quick set of problems for us to get used to using this standard normal distribution. Okay, so X is a normal random variable with parameters mu equals 10 and sigma squared equals 36. Compute the probability that X greater than 5. For all of this, my first advice is don't try to solve this problem where mu is 10 and sigma is 36 or sigma is 6. First step is what? Reduce this normal distribution problem to that of the standard normal distribution, for which we can use table A1 or appendix 1. This one here. We can use this. Sorry, I want to just copy paste this function so that you can use this table. So here we go. What do you want? You want probability of X greater than 5, right? So that's what you want. Step 1, define Z equals X minus mu divided by sigma. That is, calculate a new normal variable or calculate a new random variable, Z, which is centered at 0 and has a standard deviation of 1. So if you want to convert the statement probability of X greater than 5, okay, that will be probability of Z greater than what? That's your question. Wherever X appears, you can convert X to Z using this transformation. Just like you do in integration, wherever X appears, convert it to a Z. If X is 5, what will be Z? Z would be, if X equals 5, Z would be 5 minus, what is mu?
10.
10. And what is sigma? 6. Because sigma squared is 36, sigma has to be 6. So this gives me minus 5 by 6, which you can convert it to a decimal. It's totally all right to keep it as a decimal with, let's say, 3 decimal point accuracy. 5/6 is 0.833 minus 0.8333. With me so far? Yes, thank you.
I have a question.
Yeah.
Could a deviation be negative?
Impossible. Mathematically impossible. Deviation is defined as the sum of the squares and then the positive square root. So there is no way deviation can be negative. Okay, so if you want the probability that X takes values greater than 5, that's like asking what's the probability that Z takes values that are greater than minus that are greater than minus 0.8333. When you are at this spot where you have written down an expression for Z or Y or whatever you call it greater than something, the very next thing you should do is to draw a sketch. Draw a sketch. Where is the standard normal distribution centered? The distribution for Z centered. Should it be 10? Should it be 0?
Be 0?
0. It should be centered at 0. And you draw the bell curve. And when you say z greater than minus 0.83, let's say minus 0.83 is here. That means you are interested in the area to the right of it. You agree with my shaded area? First, you have to identify that. Yes, everyone?
Yes, can you explain why it's centered at 0 and not 10?
Because we transformed the variable from x, which has a mean of 10 and standard deviation 6. We defined z, which is defined as x minus mu divided by sigma. So by definition, it is centered at x equals mu or z equals 0. This is z, not x.
Okay, I see.
Okay. So we are interested in this area to the right of minus 0.833. Okay. With me so far? And in between here, you have 0. What is to the right of 0? Isn't this 50%? To the right of 0, you have 50% of the area, don't you?
Yes.
Right? So what you really want, which is this let's say I'm highlighting this yellow region. This yellow region is basically 0.5 plus something that you don't yet know. So the value you want, okay, the value you want is, I'll write 0.5 plus yellow. Hope that makes sense. Yeah, 0.5 plus yellow. Hey, wait, there's a very easier way to do this. Nobody told me this. I want everything to the right of minus 0.833, right? I can write this 1 minus everything to the left of it. Wait, can I do that? Yeah. I mean, all these paths will be equivalent. I just want to give you the simplest, but not always I give the simplest. I sometimes complicate things. Yeah, we'll go with what I originally had. 0.5 plus yellow. Okay. If you figure out the yellow, you can go home now. How do you figure out yellow?
You just find the positive 0.833 value and add it and subtract it from 1.
And you subtract it from 1 or 0.5. So if you take
whatever's on the right side would have to be on the left side.
right, you subtract it twice. You're right. That is yellow. The yellow areas, the yellow shaded regions value would be the function up to 0.833. Okay. Function up to 0.833. Blanking out here. Just give me 1 second. Function up to 0.833 minus 0.5 minus 0.5, right? Isn't that what I need? of f of 0.833 will be from minus infinity to that. And if I take out 0.5 from that, that will be this area, which is also equal to the yellow area. So if I put it back here, this is nothing but f of 0.8333. Am I correct here? Is it not f of 0.5? Let me see here. Minus f of 0.5. No, Thomas, I'm not sure. Give me 1 second. Sorry. Please think for yourself also. Let's you got the idea. You have as much information as I do. Let's just figure this out. So x greater than 5 is z greater than probability of x greater than 5 is probability of z greater than minus 0.833. Okay, so if I draw this, so here is minus 0.833. I need this area to the right of it. To the right of it. So that would be, this is 50%. So that would be this area. This area, which would be 0.833. What is f of 0.833? 833. I don't have it here. I have 0.83, which is 0.7967. So that would be 0.7967. So everything to the left of this is 0.7967. Okay. So this area is going to be 0.2967. If this is 0.2967, this is also 0.2967, which means the area that I want is 0.7967. So this is going to be 0.5 plus 0.7967 minus 0.5. Which is 0.7967. Did that make sense? I'm sorry, I kind of lost my train of thought there. Thank you, Thomas. Jonathan. Tyler. Eli. Elijah, thank you.
Can you re-explain it like another way? I need to hear it re-explained, I guess.
Okay, I'll do that. Thank you. So this is what we originally want, and then we transformed that to z greater than minus 0.83, which is really z greater than minus 0.83 is here. So this is really everything to the right of this line. That's what we want. You're with me? Everything to the right of minus 0.83 is what this statement means. Okay, that would be this horizontally dashed area, okay, plus everything to the right of 0, which is 0.5. This is to the right of 0. To the right of 0, and this is the horizontal area, dashed area. Are you with me, Thomas?
Yes.
Okay. All right. So this is easy. This 0.5 we already have. It's like asking what's between minus 0.83 and 0. Now, one thing that you have to remembering is symmetry. If you take this line as a vertical hinge, you can take that horizontal shaded area and just flip it 180 degrees like a page of a book. So this area is exactly same as this area between 0 and plus 0.83. That number would be whatever the value of point. See, our table is only defined for positive values. That's why we have to do all these trickeries. So that this to the left of this 0.83 is 79.67. That came from the table. This value 0.67967. So to the left of this line is everything is 0.7967. To the left of this line is 0.5. So we subtract 0.5 from 0.7967 to get this 0.2967. That's what this is. So if I then add them together, this 0.5 cancels out and gets me 0.7967, which is the probability of everything to the right of minus 0.833, which in hindsight is obvious because if everything to the left of this line is 0.7967, you can directly flip the page and show that by symmetry, this should also be exactly the same thing. Bradley?
I'm sorry, how did you get the 0.7967
That is coming from the table.
table? Gotcha. Okay.
At some point, you're going to use the table. So usually once you've figured out what's the line that you want to, that's your reference line, then you go back, look up the table. For everything to the from minus infinity to that line is given by 0.7967. Look at how at x equals 0, the table starts at 0.5. That's like saying minus infinity to 0 is 0.5. And see where the table ends at around 3.49. It's practically 1. It's almost 1. Beyond 3.4, there is actually nothing much. That's what this says. Okay, it'll get better as we do a few more examples. It'll get easier. Okay, so let's try the next part. What's the probability that x is between 4 and 16? So we'll do the second one here. What's the probability? X between 4 and 16. So immediately you can convert this to z. If x is 4, what is z? That's 4. 4 minus 10 divided by 6 less than z less than 16 minus 10 less than divided by 6. Or probability of minus 1 less than z less than 1. This looks familiar. What lies between plus minus 1 standard deviation?
68%.
68.3 or 68.26%. Okay, so that's good. Thank you. So this is, we just did this problem. This 0.6826. If you want, you can do this again. This would be exact repeat of this procedure here, where we did 0.8413 minus 0.5 times 2 or 68.3%. This is the key step, converting from a given problem to the standard normal distribution. This step, if you master, then the rest is just practice. Okay. Good. Can I do the next part? Yes. Okay. Thank you. All right. Let's do part D. We'll skip C and do part D. Probability of x greater than or x less than 20. So probability of x less than 20, x less than 20 would be probability of 20 minus 10 divided by 6 less than, I'm sorry, z less than 20 minus 10 divided by 6. For those who are a little bit lost, I'll do this very simple step here. X less than 20, right? Let's subtract mu from both sides. X minus mu less than 20 minus mu. You'd be cool with that, right? Just subtracting the same number from both sides of the inequality. And then I can divide both sides of the inequality by the same positive number, x minus mu, divided by sigma less than 20 minus mu divided by sigma. You'd be okay with that, right? Just dividing the same number on both sides. We define z equals x minus mu by sigma, and we call it the standard normal variate or random variable. So the left side is now z. The right side is 20 minus mu divided by sigma, for which I substitute mu equals 10 and sigma equals 1. That's 10 divided by 6, or this is 10 divided by 6, which is 1.6667. Or right, 1.67. So probability of z less than probability of z less than 1.67. That's what I want, which is nothing but, going back to the basics, this is integral from minus infinity to 1.67 of, I have this function here. I can give it like a variable y or x or anything. So that is like asking what is between minus infinity to 1.67 of square root of 1 over square root of 2 pi exponent of minus x y squared by 2 dy. How do you figure out this?
From the appendix?
Go to table A1, look up 1.67. Here is 1.6. Here is 0.7. So here is 1.67. Point 9525. So this will be probability of X taking values less than 20 is actually 95% chance. Are we all good? We have 9 more minutes, maybe squeeze in one more problem.
How did you know to look in the 0.7 column?
Because I want 1.67. I know there is 1.6, and if I want 1.67, I mean, it's the way they have presented the data. So they have given me
Gotcha.
0.7.
Gotcha. So that top row represents the numbers in between.
Second decimal point.
Second decimal point. Thank you.
Okay. All right. So I'll leave you to do the other parts, okay, as practice. Let's try something else. Okay, instead of looking at probability, I want you to use the table, find out the value of X, that is the 75th percentile. That is, what value of X has a value 0.75. Okay, that is 0.75 equals minus infinity to X of this function dy. What value of X will get you 75% probability to the right of or to the left of that area? So if I here, this is 0, and I'm trying to determine what value of X will be such that everything to the left of X is 75%. So should I go to the table, go to 0.7 and then 0.75? Should I take this number? Shall we do that? Shall I take this 0.7734? Is that the answer?
Wouldn't we want to go closer to 75%? Like for 0.68, there's 0.7517. Wouldn't that be a closer number?
Okay. I was trying to confuse you guys by asking or giving a false choice. I just took X equals 0.75 and it just happens to be 0.77. It's just a coincidence that this is also close to 0.5. Thank you. But what we are supposed to do is, I'm asking, should we look for X equals 0.75, or should we look for what value of X gets you close to 0.75, which is this value? So that would be like 0.68. So is the choice are, is the answer 0.75 or is the answer 0.68?
0.68?
0.68. Everybody agrees? 0.68 is what we are seeking. Thank you. Thank you. So the answer to this question is the value of x from the table from A1, x is approximately equal to 0.68. If x is 0.68, everything to the left of 0.68 represents 75% of the probability, or it's the 75th percentile. One more question. What value of x is the 95th percentile? So I want you to figure out x 95. To what value of x to the left of which is 95% of the probability? You know what? Let's not do 95 because it's very close to a number we already did. I want some weird percentage, like I want 87 percentile. I want the 87th percentile value. What is x 87? I'm saying it's 1.03. Do you agree?
It's 1.13, right?
1.13 or 03? Yeah, 1.13. Sorry, 1.13. Okay. We have 4 minutes. Let's try to do a word problem if we can. All right, a manufacturer produces bolts that are specified to be between 1.19 and 1.21 inches. If its production process results in a diameter being normally distributed with a mean of 1.2 inches and a standard deviation of 0.005 inches, what percentage of the bolts will not meet specifications? Meaning, what percentage or what fraction will lie outside of 1.19 to 1.21? So if this is the problem statement, we are seeking non-compliant bolts whose diameters, we'll call the diameter D or X. X is either greater than 1.21 or X is less than 1.19. These are non-compliant. So the compliant bolts will have a X value between 1.19 to 1.21. You are asked for percentage of non-compliant bolts. That will be probability of X greater than 1.21 plus probability of X less than 1.19, which is nothing but 1 minus probability of everything that is compliant. Everyone's cool with this? I have 2 minutes, but tell me if this makes sense. Yes? Okay. So now you are given the mean and standard deviation as 1.2 and 0.005. The next step is convert the bolt diameter X into the standard normal variate or variable Z. So where you will have Z equals X minus 1.20 divided by 0.005. So I'll just do that step for you. This will be 1 minus probability of, if I take 1.19, that's going to be 1.19 minus 1.20 divided by 0.005. That's minus 2. Minus 2 to plus 2. Probability of minus 2 less than z less than 2. I mean, you don't have to. I mean, actually, we can do this. We have like what, 30 seconds. So you want to look up between minus 2 to plus 2. Okay. I'll suggest you do it yourself, but knowing what I know about normal distribution and the fact that two standard deviations contain about 95% of the data, I'm going to write this is minus 1 minus 0.953, which is approximately 0.047, or about 4.7% of the bolts will be non-compliant. You can check this later. Yes, Jonathan, good, okay. So you can check this number, all right? Before we depart, any questions or anything else? On Thursday, we have our quiz, no more delay. We are meeting on Thursday, 2:40 p.m. And I want to be done by 3:40 and use the last 20 minutes to go over more examples. So please be on time. Any other question?
For this solution, could you use the way we did it earlier and use f of 2 equals 0.5? I mean,
You
it's
can do
f
you
of
can
2
do that. Yeah,
minus 0.5 times 2.
you can do that. You can do f of 2 times 0.5. Sorry, f of 2 minus 0.5 times 2. So this should also be equal to f of 2 minus 0.5 times 2. We can quickly check that actually. What is f of 2? F of 2 is 0.9772. 0.9772. F of 2 is 0.9772 minus 0.5. That's 0.47. No. Okay, I don't want to hold everyone up. You can try it and keep me posted. We can quickly talk on Thursday after the quiz, like at 3:40 p.m. So on Thursday after the quiz, we'll have lecture. Okay, please don't go away after the quiz. All right, thank you. Take care. Stay warm.
Have a good day.
Thank you. Bye. Thank you. Thank you. Thank you.